Hello everyone, my name is Wei Wang, a PhD student from the University of Tokyo. Today I will give you a presentation about my research entitled Effect of Reactive Aggregate on the Early Age Reaction of World-class Activated Slag or Fashion Modulus. The presentation mainly includes four parts: introduction, materials and methods, results and discussion, and the conclusions. First, I will give you an introduction of the research. As we all know, there are some problems in the traditional cement industry. When we produce the cement, we need to consume massive natural resources and much energy, and as well as it will emit much carbon oxide. The carbon oxide emissions from the cement industry consists of about 8% of the global carbon oxide emissions. Considering the carbon oxide emissions reduction goal of the world, it's necessary to think about the sustainability of the cement industry, and they are under pressure to seek ways to solve these problems. Among them, the alkaline activated materials is one of the promising alternatives for the OPC, as it can utilize the industry byproducts or the waste, and it needs less natural resources and less energy, as well as it will emit less carbon oxide during the production. Since the slag and the flash are the most commonly used material for the AM, so these two materials are chosen for this research. From the literature review, we can know that the AM can have the comparable or better performance than the OPC, but the high alkalinity activator used for the activating may raise the risk of alkaline silicon reaction when they mixed with the reactive aggregate. Up till now, few studies have been carried out to address the potential risk of ASI in AM, but the findings are always contradictory, and these findings can be divided into three groups. The first group is they conclude that there is no ASR in the AM. The second group is exists the ASR but lower than the OPC. The third group is exists the ASR and higher than the OPC. Meanwhile, compared with the ASR-induced long-term expansion and contradictory results, much is unknown about the early age reaction of the AM mixed with reactive aggregate, which is very important for the long-term properties of the AM. So the aim of this research is to investigate the effect of reactive aggregate on the early age reaction of world-class activated slag or fashion modulus, and to compare the law of reactive aggregate on the early age reaction of ordinary Portland cement system and the alkaline activated material system. This is a follow chart of the experimental procedures. The focus of this research is to investigate the effect of reactive aggregate on the reaction kinetics, reaction products, and the pore structures of the specimen. These tables and figures show the physical and chemical properties of the solid precursors used in this study. And this table and figure shows the physical and chemical properties of the aggregate used in this research. We have tried our best to keep the similar size distribution of the aggregate used in these studies. This table shows the mixture proportions of the modulus used in this research. The sodium silicate was with the silicate modules 1.5 were used as the alkaline activator in the research, and the sodium oxide content was 6% of the precursors. These are the three methods used to investigate the reaction. First, we studied the heat evolution of the specimen. From the figure, we can see that the heat evolution of the OPC mixed with reactive aggregate was similar to that of the mortar mixed with non-reactive aggregates. But for the AS and the AFA, there are more heat in the dissolution and waiting stages of the mortars mixed with non-reactive aggregate, which suggests that the reactive silicate dissolved from the aggregate. And then we use TG analysis to investigate the reaction products of the specimen. Similarly, for the OPC system, the amount of reaction products of mortar mixed with reactive aggregate was similar with that of mortar mixed with non-reactive aggregate. But for the AS and the AFA, the amount of reaction products of mortar mixed with reactive aggregate was higher than that of non-reactive aggregate. This suggests that the dissolved reactive silica participated in the early age reaction of AM and promoted the gel formation. Furthermore, we investigate the effect of reactive aggregate on the pore structures of specimen. From the figure, we can see that the porosity of the OPC and the AS mortars mixed with reactive silica was similar with that of non-reactive aggregate. But for the AFA, the mortar mixed with non-reactive aggregate was lower than that of reactive aggregate. This phenomenon may be due to the balance between the pores caused by the dissolution of the reactive silica and the reaction speed of the specimen itself. Meanwhile, we also check the porosity changes of the reactive itself before and after soaking in the water class for 7 days. From the results, we can see that the porosity of the reactive silicate was increased after soaking in the water class, which further suggested that the reactive aggregate will dissolve in the alkalinity solutions. Based on the above-mentioned results, we try to implicate of the early age reaction study on the long-term ASR behavior in the AM system. This is the schematic representation of the correlations. In the early age, due to the low alkalinity pore solution of the OPC, so the reactive silica on the reactive aggregate was dissolved less in the OPC, but for the AFA and the AS, due to the high alkalinity activator used, so the reactive silica dissolved more in them, and due to the high speed of the AS, so the pores were filled with reaction products, while the pores remains in the AFA due to the low speed of the reaction of AFA. As time goes on, the pores in the AFA was filled with reaction products, but due to the low calcium content of the AFA, so the viscosity of the generated ASR gel was low, and it can move to other place, so it will not cause the expansion. But for the AAS, as it has the high calcium content, so the generated ASR gel was restricted in the local place and accumulated the strength and caused the cracks, caused the expansion and cracks in the end. So these studies suggest that the effect of reactive aggregate on the early age reaction of OPC, AAS, and AFA are different with each other, and the dissolve the reactive silica from the reactive aggregate, participate in the early age reaction, and promote the gel formation in the early age. The funding of this research may provide a way to explain the long-term ASI behavior of the AM in light of the early age reaction. That's all. Thank you for your attention.